Given a bunch of data, an important thing we might want to do is to figure out how the data are related. For instance, suppose you have two variables, x and y, and you want to know if there's some relationship between x and y. Perhaps you think y should depend on x, or maybe knowing x helps you predict y. For instance, does the height of a father predict the height of the son? Do SAT scores depend on family income? To try to answer questions like these, you might take some data. Suppose you have a collection of, say, 100 data points for x and y, given by xi and yi, where I goes from 1 to 100. If the data looks like this, you might infer that there is some kind of approximately linear relationship between x and y, subject to a little bit of error. But if you saw a picture like this, you might be more inclined to think the relationship between y and x is not linear. Maybe it's quadratic. We can discuss both situations, but let's start with the first. If the relationship appears linear, the next thing you might do is ask, what's the best fitting line? Because if you had such a line, then for any value of x, you can use the line to make a prediction about y. So the question before us is, given n data points, xi and yi, going from 1 to n, what could we mean by the best fitting line? Let's look at one example. Suppose I have 4 data points and I'm interested in the best fitting line for these 4 points. The best fitting line is sometimes called the regression line. The data are given in this table and plotted on the xy plane. Now, suppose the equation for the best fitting line is given by y equals mx plus b. If the data fit the line perfectly, then we would expect for each data point that yi equals m times xi plus b. But in reality, the points don't lie perfectly on a line. Maybe they lie off the line just a little bit. In that case, we expect yi equals m times xi plus b plus a little epsilon sub I. Here, epsilon I represents the ith error, also called the ith residual. It says how far the data is from the line in the y direction. Notice that this model assumes the error, if any, lies only in the y direction and not in the x direction. So each data point throws off a residual, and we therefore get a vector of residuals, one for every data point. And now the question becomes, how do we minimize the residuals to get a best fitting line? And what do we mean by minimize? If we wrote the equations for all 4 data points simultaneously, we could put them in a matrix equation like this. Here the vector we'll call capital Y consists of all the little y sub i's, and it is sometimes called the observation vector, since it consists of observed values of the y variable for given x values. The matrix capital X is the 4 by 2 matrix whose rows are xi and 1. It is called the design matrix, and this design matrix may change depending on the model we choose. Later on, we'll see some other examples. The column vector MB is called the parameter matrix, and in keeping with statistical convention, we'll write this vector as beta. Beta is what we will vary in order to try to minimize the residuals. Notice how changing beta will change the best fitting line. And then the vector of residuals is, unsurprisingly, called the residual vector epsilon. This is the vector we want to minimize. And how should we do that? Well, there are many ways we could do this, but it turns out the most natural thing to do is to minimize its length as a vector. Minimizing the length of a vector is the same as minimizing the square of its length, which happens to be an easy expression, the dot product of the vector with itself, which in this case is the sum of the squares of all the individual residuals. It's for this reason the best approximation we're seeking is called the least squares approximation. Let's see how we can do this minimization. First note, from the earlier equation y equals x beta plus epsilon, that epsilon is the y vector minus x times beta. So we want to minimize y minus x beta. Well, one way to think about this minimization is that y is a point in R4. The residual vector is the vector between y and the point x times beta. So as beta varies, we are trying to find beta so that the point x times beta is closest to y. That particular beta we'll call beta hat, which is our estimate of the beta that accomplishes this minimization. Now the point x times beta hat as a matrix product lies in the column space of X. And the column space of X is a two-dimensional subspace of R4 as long as there are at least two different X values. That's a plane in R4. So we are searching for a point in that plane that is closest to the point Y in R4. And that will give us the linear combination of the columns that we seek, which is our estimated parameter vector beta hat. Now, you could use multivariable calculus to find this point if you knew some, but there is an easier way. Our geometric intuition tells us that at such a point, the residual vector should be perpendicular to the subspace. Since the subspace is the column space of X, this means the residual vector should be perpendicular to all the columns of X. One way to demand that the residual vector is perpendicular to all the columns of X is to demand that it be perpendicular to all the rows of X transpose. So X transpose times the residual vector, y minus x times beta hat, should equal the zero vector. Multiplying this out and moving one term to the other side, we see x transpose times x times beta hat should equal x transpose times the y vector. This particular system of equations is called the normal equations for beta. This always has at least one solution for beta, and we can see that this geometrically is true because there is always a closest point on a subspace to a given point. The only question is whether there might be multiple solutions. You can see it might depend on whether x transpose x is invertible. X transpose x is sometimes called the Gram matrix. If it is invertible, you can solve for beta like this. Beta equals x transpose x in inverse times x transpose times y. This is a nice theoretical solution. But in practice, when you're solving it, it's usually just easier to solve the normal equations by Gaussian elimination rather than trying to compute the inverse of x transpose x when it exists. You would then use Gaussian elimination on the augmented matrix with the Gram matrix on one side and x transpose y on the other side, and this would enable you to solve for the vector beta hat. Those who think about numerical algorithms know that solving the normal equations can sometimes be unreliable because small errors in Gaussian elimination can lead to big errors in the solution. But if you have a QR factorization of x, which we discussed in an earlier lecture, you can compute beta in a more numerically stable way. Recall from that earlier lecture that an m by n matrix with linearly independent columns can be factored as q times r, where q is m by n with orthonormal columns, and r is upper triangular and invertible. So let's suppose x equals q times r. Then take the normal equations and rewrite them substituting qr for x. you'll get the quantity QR transpose times QR times beta equals QR transpose times the vector y. Since the transpose of a product is the product of the transposes in reverse order, we see that R transpose QR beta equals R transpose Q transpose y. But Q transpose Q is just the identity because the columns of Q are orthonormal. So we can ignore the Q transpose Q in this expression. So we have now R transpose R beta equals R transpose Q transpose y. But now we remember R is invertible, so R transpose is invertible. So we can multiply both sides by the inverse of R transpose on the left, and that will cancel the R transpose, and we will have a simpler equation, which is just R beta equals Q transpose y. This can be solved for beta using Gaussian elimination, and it's less likely to exhibit the kinds of problems that the normal equations did. And if we want, we can multiply by R inverse on the left to get the very simple expression beta equals R inverse Q transpose y. This is a very nice, simple formula to do least squares regression if you have a QR factorization of x, which exists when the columns of x are linearly independent. Let's see what that means for us in our example of 4 points. Recall that the data table looked like this. And in this case, the observation vector y is the vector 2, 3, 5, 5. The design matrix X is the 4x2 matrix with columns 1, 2, 3, 4, and 1, 1, 1, 1. We're searching for the parameter vector beta with entries MB that minimizes the length of the residual vector epsilon. So we'll take a moment to compute the gram matrix X transpose X. And if you did this, you should get the 2x2 matrix 30, 10, 10, 4. And if you compute X transpose Y, you should get 43, 15. If you take the inverse of X transpose X, you'll get 0.2 minus 0.5 minus 0.5, 1.5. We'll multiply this by X transpose Y, which is 4315, to get beta hat, whose entries are M equals 1.1 and beta equals 1. So there's our best fitting line. It's going to be y equals 1.1x plus 1. And if we draw this picture, we see that it indeed seems to fit the data pretty well. Let's think about what would have happened to the matrix X transpose X if we had more data. It would still be 2 by 2, but the top left entry is just the dot product of the x values with itself. So it's just the sum of the squares of the x values. The bottom right corner would be the dot product of the all ones vector with itself, which is just n, the number of data points. The other two entries are the dot product of the x values with the all ones vector. So we obtain the sum of the x values. Similarly, X transpose Y is the dot product of the columns of the X matrix with the Y vector. So we get as its entries the sum of xi, yi, and the sum of the yi. Thus, when trying to find best fitting lines, you only need to keep track of the following 5 quantities: n, sum of the xi's, sum of the xi squares, sum of the yi's, and sum of the xi, yi. This is an advantage because when you enter the data 1 point at a time, you actually don't have to store all the data. You can just add to the running totals for each of these 5 quantities, and you have all the info you need to find the best fitting line. So as the new data comes in, you just keep track of these running totals. Well, we don't have to stop there. We can actually consider least square approximations for a collection of data for multiple variables, where we think of one variable as depending on multiple other variables in a linear way. For instance, every year the US News and World Report issues rankings of colleges that depend on some unknown way on various attributes of those colleges. The graduation rate, faculty salary, class size, reputation, etc. We don't know the exact formula they use, but suppose we want to find out, to reverse engineer the formula from the data we have on the schools and how they got ranked. And maybe we believe that the response variable, in this case the total score, can be explained by multiple other predictive variables. We might start by assuming the relationship is linear, that each factor has some unknown weighting, and we want to figure out what that weighting is. This is an example where multiple linear regression may help. To fix a particular example, suppose we have one variable, call it y, the response variable, and multiple predictor variables, u, v, and w. Suppose also we make some large number of observations, say n observations, and we've collected data, ui, vi, wi, and yi, for I equals 1 to n. Then, if there's something close to a linear relationship between yi and the ui, vi, and wi, then we expect for some as yet unknown coefficients, let's call them b sub u, b sub v, and b sub w, that y1 should equal b plus b sub u times u1 plus b sub v times v1 plus b sub w times w1 plus epsilon 1, an error term. And we expect similar equations for the other data points with error terms epsilon sub I in each of them. This can be rewritten as a matrix equation, y equals x times beta plus an epsilon vector, where y is the observation vector of y values, x is the design matrix whose n rows are 1, u sub I, v sub I, and w sub I. Beta is a parameter vector that we're solving for with coordinates b, b sub u, b sub v, and b sub w. And the epsilon vector is a vector whose length we hope to minimize, as before, in a least squares fashion. We can appeal to the same normal equations to solve for beta. And we can solve our problem in a similar way as before and find an estimate for the beta vector to be beta hat, which equals the inverse of the Graham matrix, if it exists, times x transpose y. In the normal equations, if x is n by p, note that the Graham matrix x transpose x is a square matrix of dimension p by p. Note that if x transpose x is not invertible, then beta will not have a unique solution, which will be a bad thing. So it sure would be nice if we knew when the Graham matrix were invertible. And there's a theorem for that. It says x transpose x is invertible if and only if the columns of x are linearly independent. Let's prove this by proving a logically equivalent statement that x transpose x is not invertible if and only if the columns of x are linearly dependent. I hope you'll agree both statements are saying the same thing. And a proof goes like this. Suppose the columns are linearly dependent. That means that there are coefficients that exhibit this dependency. So there's a non-zero vector v using those coefficients such that x times v equals 0. But that means x transpose x times v equals 0, which shows that x transpose x has a non-trivial null space. So by the invertible matrix theorem, it cannot be invertible. Conversely, if x transpose x is not invertible, there's a non-zero vector v such that x transpose x times v equals 0. But then v transpose x times v must equal 0. Notice that v transpose x transpose is equal to the product x times v first, then transposed. This means xv transpose xv equals 0. That's taking the dot product of xv with itself and getting 0. This means xv has to be the 0 vector for some non-zero vector v. So x cannot have linearly independent columns. We've shown both directions, and that ends our proof. This theorem is actually a pretty practical theorem. Look at the columns of x. They come from various predictor variables in the data. So for instance, if it happened that the u column and the v column were identical, then you'd expect that b sub u and b sub v would have many possible solutions. So it makes sense that you couldn't, in this case, solve for the beta vector uniquely. The key practical advice from this discussion is try reducing dependencies among your predictor variables in your data. So for instance, if you're going to collect data, you'll want to be sure you aren't doing so in such a way that's producing dependencies among the predictor variables. This will keep your regression software from throwing a fit. Also, if you're choosing to use more predictor variables than data points, which means more columns than rows in X, you will not be able to have linearly independent columns. This means that there will be unintended dependencies among your predictors. So now that we've come up with a nice linear model to explain our response variable y in terms of predictor variables, how should we answer the question, how good is this fit? Are the observed values of y close to the predicted values? Well, what are the predicted values of y? That means taking our estimated parameter vector, beta hat, and applying it to our data. You see, we believe now that the response variable y equals x times some true beta, but we only have an estimate for beta that we called beta hat. So our predicted values for that data is x times beta hat. We'll call this vector y hat. If n is the number of observations, then this vector lives in Rn. So if I made 100 observations, this vector lives in R100. The vector y hat tells us for each data point what we should have gotten if our estimated parameter beta hat were the true model. If we replace beta by our solved normal equations, we'll find that y hat is x times the inverse of the Gram matrix times x transpose times the observed y vector. Now this equation is very complicated, but it's very interesting. Do you see what has just happened? We started off with our original data of observed predictor variables in the matrix X and the observed response vector Y. Based on minimizing residuals, we got an estimate for beta that we called beta hat, and now we're using that to return predicted values of y in y hat. This crazy expression in front of the vector y is called P, the projection matrix. There's a good reason for it. It's a matrix that projects an observed vector y to a point in the column space of X where the predicted values occur if the model were really perfectly linear. So it takes y to y hat, just as we expect. We're using our original data x to turn our original response data, the vector y, into their predicted values. The residual vector is now the difference between the observed values of y and the predicted values y hat. We usually call this residual vector an estimated residual vector since we've only estimated parameters for the actual linear model, which is unknown. So we put a hat over the residual vector and call the vector epsilon hat. Now, if the data were a perfect fit, we'd expect epsilon hat to be 0. Otherwise, there might be some residuals, so epsilon hat is a non-zero vector. What we are looking for is an estimate of how large the individual residuals could be, and the best guess we have for that are the observed data. If we treat the components of the residual vector like it were a sample, then an estimate for the standard deviation of the residuals is given by using a sample standard deviation formula on the components of the residual vector. That's computed by taking s squared equals the dot product of epsilon hat with itself divided by the number of degrees of freedom here, which is n minus p. Then s is an estimator for the standard deviation of the residuals. It has a name. It's usually called the standard error of the regression. Its units are the same units as the y variable, so it's a measure of how close we can expect the predicted values to be to the actual values. So for instance, we expect most of the observed values for y to lie within 2 standard errors of the predicted values. So this gives us a good sense of how good our fit is. Well, what if the data is not linear? Suppose we want to fit data with a quadratic function or a cubic function. What should we do then, since we've only been talking about linear things in this course? Well, surprisingly, we can still use linear algebra. The only thing that changes here is the design matrix. Suppose we have variables x and y, and we think y depends in a cubic way on x, and we want a best fitting cubic. Then we assume y equals ax cubed plus bx squared plus cx plus d, and we're interested in solving for the coefficients a, b, c, and d. Well, the key here is to realize that y depends in a linear way on x cubed, x squared, x, and 1. So we can use multiple linear regression to do cubic regression. If we take the data xi, yi, and make the substitutions, letting ui equal xi and vi equaling xi squared, and letting wi equal xi cubed. Then we are exactly in the case we solved before. We can use the normal equations to solve for the parameter vector beta, which in this case is d, c, b, and a. And if you're wondering, the order of those coefficients follows the order of the columns in the design matrix. This is great. This means you can do polynomial regression of any type using the appropriate number of variables in multiple linear regression. So we've seen how useful linear algebra is for thinking about and solving the problem of finding a best fitting line or best fitting linear model to observe data. This is pretty nifty. There are plenty of other ways that linear algebra turns out to be useful in statistics, which you can learn more about in a mathematical statistics course.